So this is the today's question. So it says that let G be a group such that 3 doesn't divide order of G, and for any two elements A and B, A cube B cube equal to AB whole cube. Then show that G is abelian. Okay. So observe that x cube equal to identity implies x equal to identity, since 3 doesn't divide order of G. So if x is non-identity, that means order of x is 3. That means 3 must divide order of G, which is a contradiction. So that means x cube equal to identity implies x equal to identity. So to show xy equal to yx, we can show xy x inverse y inverse is identity, which is equivalent to showing xy x inverse y inverse cube is identity. Okay, and now xy x inverse y inverse cube equal to xy x inverse cube times y inverse cube from given condition, which is same as xy cube x inverse times y power minus 3, right? That means xy cube x inverse y power minus 3 is identity if and only if xy x inverse y inverse cube is identity, if and only if xy x inverse y inverse is identity. That means x commutes with y cube, x commutes with y cube is equivalent to showing x commutes with y. Right? Okay. Now I claim A square belongs to center of G for all A belongs to G. Okay. We know AB cube equal to A cube B cube, right? That means AB equal to A cube B cube. That means BA, if I cancel A both sides, I will get A square B cube. Similarly, BA cube equal to B cube A cube. BA equal to B cube A cube. If I cancel A from right side, I will get B equal to B cube A cube, A square. So from 1 and 2 I get A square B cube equal to B cube A square, right? That means A square commutes with B cube, which implies that A square commutes with B. And here A and B are arbitrary. So for any fixed A square commutes with all B. So we can take any B here. This will imply A square belongs to center of G for all A. Now we have AB cube equal to A cube B cube. Which implies that AB equal to A cube B cube. That means BA square equal to A square B square. Now A square belongs to center of G, so that will imply A square B square equal to B square A square, because they are common. right? So that means B B BA BBA times A equal to B, sorry, that means from this BA equal to BBAA. Cancelling B and A both sides, I will get AB equal to BA. And here A and B are arbitrary because we know that for any A square belongs to center of G. So you can take A and B to be any arbitrary. Hence, G is abelian. Okay. So this is the solution. Now the question says that what about the other part? Suppose G is a group such that 3 divides order of G and A cube B cube equal to AB cube. Then does there exist a non-abelian group? Kind of its converse. Yes, there exists. So let's take a non-abelian group of order 27 having every non-identity element of order 3. Okay, order 3. If you can find such a non-abelian group, okay, then since every non-identity element has order 3, that means A cube is identity, right? So, and AB cube is also identity. So, which is same as identity times identity, and A cube is also identity. So, this is trivially holds there. So, can you give some example that satisfies this? Like group of order 27 having non-identity element of order, every non-identity element have order 3. You can take this group. You can show that this forms a group and every non-identity element has order 3. And this order is 27, right? Because possible choice of A is 3, for B is 3, for C is 3. So number of elements of order G has 27, and 3 divides 27 definitely. So this condition holds, but this is a counter example. Okay. So if this condition is removed, that or G is a group of order G be a group such that 3 doesn't divide. That means even if it is satisfied, G may not be abelian. So this is an counter example, like converse statement kind of thing. Okay. I hope it is clear. If you have any doubt, you can ask me.